Oh.
Hello, hello. Okay. I think we're all right.
You can also minimize the top right.
Thanks. All right. Yeah, thanks for coming. I'm Victor. I'm an ML engineer at Suno. I think my talk or workshop is going to be very unscripted. I'm just going to go through a hack I did last month over a weekend. It's the kind of thing I'd love to see someone do today or over the weekend. But yeah, I just want to talk about I guess first, I think it's pretty self-explanatory. So let me just play the end result what we'll build up to. So basically, it's like a game of Pong, but the bounces of the ball are synchronized to the beats of the song. Yeah, I think you have an idea of what's happening. But yeah, just after 5 seconds, does anyone have an idea of how you would implement something like this? Yeah, it's not so obvious at first thought. And so I guess the way we got here was I was thinking about music visualizers because, of course, I work in music at Suno. We are always trying to think of ways we can deliver more engaging experiences to users. We generate music. We'd love to generate visuals that go along with them. So I just think about this all the time in the back of my head. And at some point, I was thinking about the Atari games, which are just these super classic arcade games like Pong, Tetris, actually probably not Tetris, but Snake, these really simple games that everyone's familiar with. And because everyone's familiar with them, it's they're really good targets for music visualization because they're familiar, everyone can understand what's going on immediately from a video. You don't have to explain it to them. And I think that makes for a really compelling visualization. It's just very intuitive. And so I was thinking how can I synchronize Pong to music? And the original game of Pong, it's you have, let me do some diagramming. You have your screen, you have your paddles on the side of the screen. And basically your paddles just move up and down to hit the ball. Like a ball. And your ball is just constantly bouncing left and right between these paddles, right? And it's just a constant kind of rhythm. It's just boop, 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 boop. And we'd like to synchronize that to a beat somehow. But as the original game is, we don't really have the degrees of freedom necessary because it just goes boop, boop, boop at a constant rate. So I was thinking how can we add some degrees of freedom to the game to make it more interesting? And this is the really awesome thing I love about computer visualization, which is you can bend the rules as much as you want. The only goal is to make it look good at the end of the day and make something that people like to watch. So what I came up with was we'll just let the paddles move on the x-axis as well as the y-axis. So in that way, we can move the paddles closer together, and then the ball will bounce faster, corresponding to an increase in tempo in the song. And we can move them further away to decrease its tempo accordingly. I guess the to make it a bit more just visually nice, we'll kind of make it like a game of air hockey. So there's like a halfway line, a midline, and we'll just limit the paddles to be on their side of the field. And with this formulation, let me actually just make it look a little nicer. Yeah. So yeah, I guess we'll just define, I'll just go through some of the physics that are in the base game, and that we'll use. So the ball will just move at a constant speed. And it'll bounce off the edges, or at least the top and bottom edges. So it can like go like this. If we hit at we can control the angle it flies at when we hit it. So like we could make a really steep vertical angle. So it goes like bounces a lot before we hit the next paddle, or it could hit it more directly on a direct path. And it's just it's really important to keep the physics of the game like pretty simple and understandable, because as humans, like we really are good at predicting the next frame, and when the physics don't like match up, it's very jarring. So it's generally a very good idea to keep physics as simple as possible and consistent. And so with those simple physics, what controls we do have are how we move the paddles to like actually intercept the ball at the right times to sync up with the song. And so this is not it's not immediately obvious that this problem is even possible. Like, let's say we have like a song that goes like and then has like really long notes afterwards. So it's like like in order to do something like that, like to do really short notes, we need the paddles very close to the center, so there's a short distance between them, right? So the ball can bounce really fast between them. And for long notes, we probably want the paddles further apart. Whoops, let me not destroy the field. So that the ball has more time to travel between them and yeah, hits the notes at the right time. So you'll notice like our screen is finite. Unfortunately, we have a finite screen space. So like if a note is super long, if we just hit it directly, we won't be able to match the duration we want, because we'll have to hit it at some point. But the cool thing about Pong is, yeah, we have this bouncing effect on the top and bottom edges. So you can think of this bounce as essentially giving us infinite vertical space, because if we just hit it at a really steep angle, we can increase the distance traveled pretty much infinitely until we get the desired duration. So in that way, long durations are no problem, and short durations are no problem, because yeah, we just move them really close to the center. So hopefully I've kind of convinced you that this problem is at least possible in theory, that like we can synchronize any song we want with these physics. There's actually a little bit more complication, because the explanation I just gave is for a single note, but a song is made of many notes chained together, right? So if we have a really long note followed by a really short note, there might be issues chaining them together. So like if we had a long note where the paddles are really far apart, and then the next note is like immediately after, this paddle can't come over here to like get the right distance. At most, it can move this close to the other side of the field. And this ball, like no matter what we do, it has to travel. The shortest path is a straight line, and it has to travel in a straight line to reach this. And it might be too long if the note is really a short duration. So it is actually a bit tricky to schedule to make sure the whole song is possible. There are some more constraints. Yeah. Are there any questions so far? Yeah, I'd just like to pause. All right. Yeah, so we've got a non-trivial problem here of like, how do we actually position the paddles so that the whole thing is possible and also probably hopefully looks good. And looking good is a very, very fuzzy constraint. It's not like something you just code, make it look good. Well, I guess with like Claude, you can do it now, but it's not immediately obvious how we would code this up. But it turns out there's a really nice kind of class of problems that are defined in a similar way called constraint optimization. Raise your hand if you've heard of constraint optimization before. All right, seems like a few people. But yeah, constraint optimization is essentially you can define some variables that you want to optimize and then some constraints on those variables. Constraints being just equalities or inequalities based on those variables. And then you specify an objective function that you want to maximize or minimize. And as long as your constraints are linear, you can do something called linear programming, which is a very classical type of problem that we have very good solvers for. As long as your constraints are linear equations or linear inequalities, and your objectives are either linear or quadratic, we have very good algorithms that can optimize these and just magically spit out variables that satisfy your constraints. And under the hood, there's many ways to do this. There's like the simplex algorithm, there's gradient descent, but essentially as long as they're linear, yeah, this problem is actually quite easy. So what we can do is we can formulate our game as a system of linear constraints and essentially move all of this work of figuring out where to place the paddles to our linear programming solver, which is great for us because it saves us from having to figure out the algorithm and learn how to do dynamic programming and stuff, and just offload all of the thinking to the computer, which is in general a very good thing to do, especially if you work at an AI company. So yeah, I guess the basic way to do this is we have some inputs, some constants that we're going to feed into our solver. So like our constants might be like the speed of the ball. It might be the width of the screen. It might be and the duration, the note durations of the song we're trying to sync to. So these will be our inputs, and we need to give it some variables to optimize. So like the variables we'll give it are what we're after is the position of the paddles at each time step, so they hit the ball at the right time. So like we can just denote every hit of the ball. We'll denote like the position of the paddle at this time step to be I guess P of I. Like, and then let's say the next time step, the position of the paddle will be P of I plus 1. And so we're trying to solve for these P of I's for all I's for the number of notes we have. So I guess our variables are, yeah, P of I, which is the positions of paddles. And we also need to figure out the angle that we want the ball to fly at after each hit. So for angle, to make things linear, we'll just encode the x velocity. And from the x velocity, we can compute the angle just with the Pythagorean theorem. That's all for the variables. And then we need some constraints on these variables. So we'll have some basic constraints just on physics. So like we know the horizontal velocity needs to be smaller than the total velocity of the ball. And we'll just define to always be positive to be easier to reason about. And also just from the definition of our game, we want to keep the paddles within it's in its half of the field. So if we say the width of the field is like W, that means we want the P of I to always be less than half of W. And also needs to be positive because we'll define it as the distance from the center. And this is all the physics of the game we've described. So it's literally just two inequalities, and we have all our physics encoded. The next thing will be our synchronization objective, which is we want the time it takes the ball to fly from here to here to match some duration that we've input. So the duration, we'll just call it like d of I of the ith note. And we want that to equal, so we can just do some math. The time it takes the ball to fly from here to here, it's the distance, which is p of I plus p of I plus 1. Distance times velocity, which is vx of I, which is another variable we defined. And yeah, so this constraint is all we need to make sure the ball flies at the correct duration. It was honestly really crazy to me that it's just one equality added to the rest of the game. And finally, we have our objective function that we're going to optimize. So for the objective, like we could feed in any objective, and if we fed this to a solver, it would now give us like valid positions for the game. The problem is not all games look the same and look appealing. Like there's degenerate games where all the paddles are just always close to the center like this, and the ball is just like stuck in the center, and it just kind of gets vertical distance by bouncing a lot in the center over the midline. We kind of want to avoid these degenerate solutions because that's not a very exciting YouTube video. We'd much rather the ball be moving across the screen a lot, so the paddles be like having to race over to like catch the ball. So I guess one way to do that is to make our objective just maximize the horizontal distance between the paddles as much as possible. So we can just directly specify that by just saying like maximize the sum of all of our PIs. And that'll just encourage the ball to move as much as possible within our constraints. And yeah, this is all the math we need for what we want. It's actually extremely simple to turn this math into code. I ended up using this library called CVXPy. It's a Python implementation or API for these kinds of solvers. And it's really intuitive to just define your variables, and then define your objective. It's very Pythonic. You can specify as many constraints as you want. And at the end, you just call problem.solve, and it'll give you all your, it'll just spit out the optimal solution for your whatever problem you have. And just to give you this is the final code of the solver. It's this one optimized Pong function. So you can hopefully follow it from and directly map the math we just wrote down to the code. So like first we figure out our durations of each note. We define our variables for the positions of the paddles and the velocity of the ball. And then we just have an array of constraints. So we have our, constraining the paddle positions to the right side of the screen, constraining the ball's speed to be reasonable. And here's our synchronization constraint that does the magic of synchronizing the game. And it's, we have our objective, just minimize the sum. And finally, it's just problem.solve. And it just spits out all the information we need for the final result. This was, I guess we can just go back to see what it spits out. I think there's some better examples. Yeah.
The last line, the first problem.solve, what is that doing?
Yeah, so all this up here is just to define our problem. We're we're just defining our problem in a way that CVXPy can understand it. And so here's where we actually construct the problem from the objective and the constraints. And once it has the problem, CVXPy, well, it has a whole library of backend solvers it can pull from. It'll figure out which solver to use and then just run our problem through the solver and then return us the solution.
What's the solve? Is that a method of the library?
There's many ways to solve these like linear programming type questions. There's the simplex method, which is very classic. There's gradient descent. The nice thing about these kinds of problems is they're convex, so which makes them easy to optimize. As long as you have the gradient, you can just follow the gradient and you're guaranteed to converge to a minimum value at some point. Yeah.
Does this actually leverage any of the Suno APIs?
No, this is just this is self-contained 300 lines of code. Yeah, just for this project. Yeah. Just a fun hack I did over the weekend.
More like a passion project.
Yeah. I hope eventually, like, I want to get better visualizations into our product. So I'd love to have something like this eventually, as we to ship out. But no, I just find this sort of thing fun mostly. Yeah. Yeah. Open to any more questions, but that's essentially all I have. I just hope this inspires some people to explore more visualization techniques. I think there's all sorts of like interesting visualizations that haven't been implemented yet. I'm an ex-competitive programmer, so it was just super cool to be able to like apply an algorithm to music and have a fun result at the end. Yeah. Any more questions? I also spent way too much time just watching these sorts of things. It's kind of addicting. Yeah. I guess one other cool thing I did was this works great. So right now I'm feeding in MIDI as inputs because MIDI you have exactly the note times, so it's very easy to extract. But I also wanted to get it to work with general songs. So like here's a song that's not just MIDI, but it's a whole different problem. How do you extract the beats from a song like this automatically? And I ended up cheating and I ended up just using the Osu API. So people have already mapped out the beats in rhythm games, and you can just take the beats from the rhythm games and plug them in, and it works pretty decently.
Yeah, I guess following on that, like you were able to do this, but not only MIDI songs. And I feel like if users could create their own songs and then see like the Pong like animation right then, that would be a really cool feature.
I think so. I really want to train an AI to eventually extract the beats automatically. I think it's totally doable. And to be honest, I think it's just the first iteration of this. Like this is kind of a minimal viable visualization. Like, yeah, it's 2 lines and a ball on the screen. I think there's a lot more to build on top of this in the future. Maybe like have pitch correspond to something in the visual. Maybe have multiple paddles, like one per instrument or something. I think there's a lot of potential here to build on top of it. Actually, speaking about that, yeah, this whole project is open source. It's 300 lines of Python. If you Google Song Pong, you can probably find it. But yeah, and also, yeah, this was a very unscripted post. If you would like to learn more and understand the math a bit more deeply, there is a blog post on my blog that just runs through what we just talked about, but at a more reasonable pace.
Thank you so much.
Thank you.
Yeah.